welcome to my talk. Today I want to talk about how you as an embedded Linux developer can use Labgrid to work from home. First, a few words about me. I'm Chris Fiege and I'm a senior hardware developer at Pengutronics. I'm currently tasked with the development of hardware for the remote control of embedded Linux devices in our lab. So my day-to-day job is working on the hardware side of the software we are going to talk about today. If you want to reach out to me, feel free to drop me an email or follow me on Twitter or GitHub. A few words about Pengutronics. We are an embedded Linux consultancy and we're having roughly over 30 employees, and we are based in the northern part of Germany. And we support our customers with all parts of their embedded Linux development. So starting from bootloader porting, writing drivers, supporting them with graphics integration, and integrate all those topics into one BSP. We have customers from all industries, so the hardware we are getting from our customers to work on is really diverse. And to ease working on these hardware, we're operating over 60 lab places that are fully automated and allow us to remote control our customers' hardware. This presentation will consist of 3 parts. The first will be a short motivation. Why do you want to have lab automation? The next one will be a short overview over the architecture of Labgrid. And the last part and the biggest part of this presentation will be demos. So, speaking generally, what do you need to control an embedded Linux device? Well, you need to be able to remote control and to interface with the most relevant interfaces of this device. And those are at least the power supply and a serial terminal to talk to your bootloader Linux system and your application on top of that. At least for development, even if you do not want to ship that in production for various reasons. The next part you may have is GPIOs. You may want to be able to press a reset button or to press a user switch, or maybe just change the boot mode of your embedded CPU. And you probably want to have access to Ethernet, to your lab network, because that probably allows you to boot your embedded device remotely instead of jiggling your SD card every time you have built a new firmware image. And depending on your application, you may have lots of other interfaces. Maybe you have SD cards for data storage or for updates. You may have a USB port as device or as host role, or a CAN bus interface if you're doing something from the automotive area. Or, well, if your device under test has a display, you may have some kind of display port on that. Depending on your hardware, well, you can have a lot of other interfaces, so this list is by far not complete. But why would you want to automate working with such a device under test? Well, first of all, one main part for me and for a lot of my colleagues is you want to avoid all those reoccurring simple tasks that you otherwise would have to do 100 times a day, like, well, taking a micro SD card out of your device under test, putting it into your card reader, and putting it back into your device under test again. Doing such simple tasks over and over again not only allows you to make more errors, on the other hand, it costs time and money. So if you would have a solution to automate such simple tasks, well, you would probably be faster and cheaper. Another reason for us is hardware is usually a scarce resource. So we have usually just 1 or 2 pieces of hardware of one specific prototype version. Well, just because our customers do not build hundreds of prototypes if they don't know if they work after all. So we have to share those hardware between our colleagues. And usually, well, we just work on one and keep the other one as a code spare as far as possible. And that means if your hardware is just on your desk, your colleague won't be able to support you. And that's maybe okay if you're just waiting for input or feedback from a colleague. But if there are multiple colleagues working on the same project, you need to have a way to share this hardware between your colleagues. And if you have a way to share the hardware between your colleagues, well, without moving it physically to another desk, you're maybe already at a point where, well, it doesn't matter if your hardware is on your desk or your colleague's desk or in a room down the hallway, or, well, maybe if you're not in the office at all and if you're just working from home or working from the small cafe down the street. And last thing automation enables you to do is testing. If you have fully remote control and you don't need to touch your device after all, you're totally free to write tests that tests a specific unit of your software, maybe a feature of your bootloader. Or well, you can also do integration tests where you test your complete software stack, including your application, with your real BSP on the real hardware. Yeah, and that is where Labgrid comes into play. Labgrid is a Python library written in Python 3, but I don't think you have to say that anymore. It's licensed as LGPL 2.1, so it's a real open source project. You can find it on GitHub, and the documentation is rendered to labgrid.readthedocs.io. Labgrid was initially heavily sponsored by Pengutronics, and still is, but it is intended as a real open source project. So we really intend to get contributions for our community, and that is really happening. So there are people out there using Labgrid for their lab automation, and they are contributing back drivers and infrastructure into Labgrid that, well, everyone can use after all. How does Labgrid work? Well, Labgrid is a hardware abstraction library for all your lab automation devices. So on the one side, Labgrid knows how to talk to your lab automation. For example, if you have a serial port that is connected via USB, Labgrid knows how to interface with it. If you have a serial port that is connected to some kind of network-based appliance and that maybe has multiple of these serial ports, Labgrid possibly already has a driver for that. Same for power switches. There are lots of off-the-shelf power switches you can just buy and use to automate your lab. And well, Labgrid probably has a driver for that. And if it doesn't, you're totally free to contribute one to a project. And I'm not going to go over all the other drivers here. If you want to have a look at what devices are supported, take a look into the documentation. There's a whole section on which drivers are supported and which features inside these drivers are supported. Labgrid has 3 ways of interfacing with the lab environment. The obvious one, and the one you're going to use during interactive development on a device under test, is the command line interface. Well, in the command line interface, you can just interactively from your shell on your device control what's happening on the device under test. And since Labgrid is just a Python library, you can also use Labgrid as a scripting interface to control your lab automation. Just imagine you have to reproduce a bug that only happens once in 1,000 times. Just write a script for it, do whatever it needs to trigger that bug, and just wait for this 1,000th try. And if it happens, just leave your device on a test in that state, and you're free to take a look what happened there. And the last part Labgrid provides is a PyTest plugin, so that you are able to write your test, be it unit or integration tests, in PyTest, just like you would for every other Python-based software. But now you're not testing, but now you're not testing a piece of Python software. You're now testing hardware instead. So, what's Labgrid's view on your lab? First, the scripting interface, command line interface, and the PyTest plugin are all clients in Labgrid's sense of the world. And these clients connect to a coordinator. That's a central service that keeps track of, well, what hardware is available in your lab and which client is currently using which of these hardware. The other part of Labgrid that connects to the coordinator are the exporters. Exporters are pieces of software that control a bunch of resources that are available in your lab. And well, resources are all those lab automation devices you have. And well, in the end, the clients will connect to the exporter using SSH. So as long as you're able to reach the exporters and the coordinators, you're free to work from everywhere. Just two more words before we start with the demo part of today's presentation. One thing I will mention during my demo is places. A place in Labgrid is a group of resources that you usually use for a place, so one device under test. But a resource can be part of multiple places. That's totally fine for Labgrid, because Labgrid has a mechanism of locking. So if you lock a place, you lock all the resources that are allocated to this place too. And so no one else can use them. And the other word we'll need later on is target. So a device under test is just called a target in Labgrid. And that concludes my theoretical part for today. And now let's switch over to the demo. Today's demo is built around this Raspberry Pi that is running as our test server. This is where Labgrid is running and where I'm currently connected to via SSH. Our device under test is this BeagleBone Black here, together with this spinning wheel motor assembly that we'll use later on to visualize an application. This device here is a USB SD mux that is used to switch a micro SD card that's, well, on the lower side of this device into this device under test, or otherwise to our test server or Raspberry Pi here. That can be used to automatically fill our micro SD card if we want to. And this assembly is generally proposed inputs and outputs, and we are currently using only one of these input and output devices, and we're using that to switch to the power of this BeagleBone Black here. So this is our power switch. Okay, now let's take a look around. We start with the command line interface. And let's have a look at the available resources here. There are 3 resources available to this Labgrid client. One is the I/O we have here that we use to switch our power later on. We have this USB SD mux, and we have got a network serial port that is the debugging serial of this BeagleBone Black here that is connected to our Raspberry Pi via USB. Okay, I have pre-configured all these resources into one place, and this place is called Motor Bone, well, because BeagleBone Black and Motor. And if I take a look at this place, we will see that there are all these 3 resources selected, and this place is currently locked by me, so no one else can use these resources. Let's skip all the other informations for now. Well, to control our target, we will use a configuration file that is written in YAML for Labgrid, and this configuration file describes how we interact with our device on the test. First of all, we select all resources that are provided by the place Motor Bone, and afterwards we stack a few drivers on top of this place. First of all, a driver to use the USB SD mux, one driver to control our network serial port, and 2 drivers on top of the serial port, one to control a shell that is running inside Linux, and one to control a shell that is running in our bootloader, and our bootloader is Barebox. You see that we have some special configuration here that tells the driver how our actual prompt looks like, so that our driver is able to adapt to different prompts and different setups. Last two drivers here are a driver for a general purpose output and a driver on top of this output that we'll use to switch power. The last thing mentioned in this configuration file is a strategy. A strategy is a Python file that is usually tailored for your device under test, and this Python file contains a state machine. This state machine is used to mimic the states that your device under test can have. For example, our BeagleBone Black can be in its bootloader, then this would be a state in the strategy too. And our BeagleBone Black can boot into Linux. So this is another state that we have defined in the strategy. The strategy then knows how to transition between these states. For example, if we want to enter the bootloader, we power on our device and interrupt the auto boot of the bootloader just to get into the shell of the bootloader. And if we then want to switch into Linux, well, we just use the auto boot feature again and wait until we have reached a interactive shell in Linux. With this configuration, I can now interact a little deeper with our place. For example, I can use this configuration and tell our device under test, well, please go into our barebox mode and give me a console once you've reached that. To reach this state, we'll first switch our device under test off. Then we will provision the USB SD mux to switch its SD card to the device under test. And afterwards, we'll power on our device under test. And well, while I'm talking, we've already reached the interactive shell of our bootloader. Well, we can do the same with a Linux shell. That takes a little bit longer. Again, power cycling our device under test. Then, if you have a look at the heartbeat LED, it shortly flashes for the bootloader, and afterwards, well, we are currently booting Linux. And just takes a little moment, and here is my interactive shell. And now I can have a look at the running Linux system here. Okay. Another thing I want to show you is scripting. I have prepared a short script here, and that brings me back to the example with, well, you may have to try a thing a few times until you trigger a bug, because it just happens from time to time. And that is what the script is about. In this script, we will again use our place configuration that I've shown you earlier. We will interact with a few drivers that we have defined in this environment, in this configuration. Well, and now we start just scripting. First thing we do is we power off our device on the test and bring our USB SD mux into a defined state, so we are clear to boot. And now for the next 1,000 times, we'll just power on our device on the test, capture our device in the bootloader, and then, well, for the sake of simplicity, let's assume there is a bug in this version command that we want to find. So we will just execute this version command and check if it was successful. Well, if not, we'll just end the script and leave our device on the test in this broken state so we can have a look what happened there. Otherwise, we'll power off our device on the test, wait a brief moment, and start all over again. Let's just run this short script. Again, our BeagleBone is powered off and afterwards powered on again. And now, I guess it's just roughly once a second, we're going to boot our device on the test into the bootloader, execute the command, check the return code, and if the return code is okay, we'll just start all over again. I'll just interrupt this here because I don't think there's a bug in this version command. Okay. Last thing I want to show you today is automated testing using Labgrid on real hardware. For this, I have prepared a PyTest test module that contains a few tests. For all of you knowing PyTest, I have defined a few fixtures. A fixture is a short function that I can use later on in my tests as a shorthand for specific features or inputs I want to use for this test. And so I create a strategy for every state I want to reach inside my strategy. One for the barebox state, one for the shell state, and one for the off state. And now I can just start writing tests like I would write tests for some simple Python script. For example, this test will again run this ominous version command inside our bootloader. To do so, we will use the barebox fixture. By using this fixture, our target will be in the state barebox once we start the test. We will run the version command in our bootloader shell. Just check the return code like we did in the script before. And if everything is fine, our test will be okay. Otherwise, test will be fail. We can do the same in Linux. For example, here, using the in Linux fixture, we will force our device under test into the state Linux, and then we can execute a command inside the Linux shell. In this case, just uname -a, so we can see what kind of kernel is currently running. We do some checks, and if all checks are okay, the test is okay, otherwise our test is failed. And last but not least, a few tests here that will spin up the motor on our test assembly. Those tests will spin the motor to a specific speed. I think it's pulses per second we see here. And if the controller, the speed controller running on the BeagleBone Black is able to reach its target, test is okay. Otherwise, the test will fail. Having a look at the clock, I'll just give this test suite a quick spin and I will tell you the other relevant parts where we are running it. So again, our first test will be running in barebox, so our device on the test will be powered off again, powered on again, we'll capture it in the bootloader and execute our test. That was successful. Next test will be running in Linux, so we're now waiting for Linux to boot. That was successful too, and now our speed controller starts spinning our wheel here. And well, for this last test, I'll just break this wheel down to a speed that's definitely below the speed it wants to reach. So, well, just to provoke a failed test here. That takes a short moment, and well, our test has failed. So you see how simple it is to write actual tests in Python that control real hardware. And that's about it. Thank you for listening. And I'm now available for more questions.